All right, how's it going? Good. So, questions, stacks, queues, PA2. PA3 is going fine. Definitely be starting PA3 by now. Awesome. Say again? You talking about handling your stack versus queue mode?
Yeah.
Oh.
You just have two variables, and you like add or B, you can check which one represents whatever, and see if it's like 0 or 1.
Yeah, and it doesn't have to be global, right? It's just inside your main program.
Yeah.
And if you're doing a stacky thing, call your stacky code. And if you're doing a QE thing, call your QE code. All right, so I wanted to talk about Makefiles first of all, because everybody's turning in Makefiles, which is awesome. And your Makefiles work to make your file, which is also awesome. But I'm seeing a lot of different versions of Makefiles, and a majority of them are probably not exactly what we want in a Makefile. So I'm glad the Makefiles are there. I'm glad that you can say make and it makes an executable. That's definitely like the most important part. But let's go back and revisit kind of the idea behind a Makefile, because the goal is to be able to edit your code, and whatever you edit, if you want to rebuild your executable, you just say make. And it compiles the right things to do that, and hopefully doesn't do more work than it has to. So let's look at a general Makefile. What? Oh, details, man. There we go. Thank you. So basic structure of a Makefile, it's a series of pairs of lines, okay? So these lines come in pairs of 2. So the first line is target, colon, dependencies. And the second line is a tab, followed by a recipe. And these just get repeated again and again and again. Okay, so what's a target? It's something that you want to be able to build with your Makefile. So it's the name usually of some file you're hoping to create. So for PA2, right, maybe your target is just called main, colon. And you want to say what pieces of my project need to be up to date before I can build main. And then my recipe is going to say, given those pieces, what do I actually do to build main? So here's one thing that will work. I need all my C files to be up to date and present in order to build main, and then the actual recipe is just gcc-o main, a.c, b.c, main.c. Okay, that will work, but here's what happens. Anytime that I change any of my .c files and I say make, it's going to execute this command. If I change a.c, which is a 5-line function, it's going to recompile a.c, it's also going to recompile b.c, and it's going to recompile main.c. Okay, so you could do the same thing by just making a 1-line bash script that just executes this gcc command. And anytime you change something, you just run that bash script. Okay, it gets you an executable, but it's not as kind of nuanced as it might be. And even if you have things down here like, you know, a.o, a.c, gcc-c, a.c, b.o, b.c, gcc-c, b.c, main.o, main.c, gcc-c, main.c. None of this stuff ever gets used. Because if you say make, it looks for the first target, which is main. It says, how do I build main? All it needs is the .c files, and then it executes this command. It really doesn't care whether or not you have an a.o or a b.o or a main.o. So these look right, but none of them are going to have any effect. Okay, so a better way to do this is to say, to build main.o, I need these object files to exist and be up to date. And if I have those, then here's the recipe I can use to build main. And gcc-o main with a bunch of objects after it, that's a very inexpensive operation. That's just taking your stuff and kind of linking it together. So this main program said call add. And when you compile this main program, it doesn't know where add is. When you compile add, it's just a function. It's not being called by anything. So when you say this, it's linking those together, and it's saying, okay, I'm going to put add right here. And over here in main, when I say call add, I'll say call this location, because that's where I put add, right? So it's just kind of filling in a few blanks. So that's a very inexpensive operation compared to compiling these C programs into objects. So when you write your makefile like this, right, if you change this one function a.c, it'll say, okay, a.o might be out of date because it depends on a.c, and a.c changed. So it will execute this command, which compiles a.c, the small 5-line function. And you didn't change b.c, b.o is up to date. You didn't change main.c, main.o is up to date. Now all three of these dependencies are satisfied, and it goes ahead and links them together. And if you say make again, right, it's going to look at this and it's going to say all of these dependencies are up to date. So re-executing this command is not going to do anything, and it'll just say, you know, everything's already up to date, and it won't do any work. So that was one thing I saw was having the .c's up here, so it always recompiles everything, sometimes with these other lines so that they didn't actually have any effect. And there were some other things I saw where you would change a .c file, but let's see, I think it said something like, what did I see? I don't remember how it was, but anyway, you changed the .c file and you said make, and it said everything was up to date because one of these wasn't listed as a dependency. Oh, I remember what it was. So I don't remember what it was, but it was something like that. And I changed a subroutine, right, a b.c, and I said make, and it said everything was up to date because it didn't know that main depended on that. So I would recommend experimenting with makefiles, right? Make yourself a directory somewhere. Just make a main program, make a couple of functions that are called from it. So you have a main and 2 or 3 functions, and put together a makefile and make some changes to it and get really comfortable with what it's doing. Okay, if you change one file and you say make, it should recompile the right pieces and then build the executable. So experiment with that. All right, but everybody gave me a makefile. The makefile worked, which was great. And the PA2s looked really good. Okay, so they did what they were supposed to do. In the majority of cases, there were no memory leaks. In almost all cases where there were memory leaks, I think it was just the Sentinel, because there was a single block not being freed at the end of the program. And it's usually an indication that in your free all, you're somehow not picking up either the first node or the last node. right? That's a really minor issue. Okay, I'm not worried about that. But you definitely want to go back and sort of figure out where that last node is coming from, right? And one quick way to tell if it's a sentinel is you just run into your program, exit immediately, and see if you've got a memory loss. And if you do, then it's got to be the sentinel, because you haven't inserted anything into your list. Or it's a case where you're malloking and then reassigning. All right, so yeah, PA2 looked good. Main programs worked well. Add, search, delete, all worked the way they were supposed to. So that made me very happy. So nice job on PA2. All right, comments. Most people are commenting well, which I'm really happy to see. And you may leave this class and never write another comment, right, until you start coming back in spring or you go somewhere else. But being able to write good commenting is important, right? And you may decide at some point that your code is self-explanatory to you and you stop writing comments, and that's okay with me. But being able to do that when you need to do it for a course or for a job, that's really, really important. So the commenting, I'm really happy with. Other things I wanted to say. Make sure your output looks the way that I ask it to. There were a few cases where the output was coming out one node per line, or where I was getting like extra information telling me about the node and stuff. And I didn't take off for that this time, but I will going forward. Okay, so on PA3, for example, I want the stack and queue, all the numbers on one line separated by spaces, and I specify which end should be on the left. And I'm going to adhere to that. So I will take off points if you print stuff on multiple lines or extra information with the nodes. So stick to that. What else? Makefiles were good. No corrupted zip files. So that was good. No corrupted tar files. There's one other thing I was going to say. Oh, okay. So, oh yeah, so this is what the other thing was. Did everybody test their program with valgrind? Right, presumably, unless you really like taking chances. So in some cases, you run valgrind, and at the end it says all blocks freed, no memory leaks possible. But while you're running your program, it's spewing out a ton of output, right? Did anybody see that happen? Right? So, so I didn't take off points for that in itself. But that got me to look a little more closely at your code. And if I saw something not quite right in there, then we started getting into some issues. So the most common incident of this was when you're freeing nodes, if you do something like free temp, and then you say previous next equals temp next. You may get away with that, but that's technically not correct, right? Because once you say free temp, this thing we call temp is now suspect. It's not necessarily the same node that it was before you freed it. It might have been reused, your free might have cleared it, any number of things could have happened, and trying to reference a field from the thing at that location in memory is going to cause you problems eventually. And that's one of the things valgrind will complain about while you're running. It'll talk about accessing inside an unallocated block or something like that. Other things that valgrind will complain about, malloc size of struct node allocates enough memory to store a struct node. If you malloc size of struct node star, you're only allocating 8 bytes. It's not looking at how big a node is. It's looking at how big a pointer to a node is, which on our server is always 8 bytes. So if your node needed to have 1,000 bytes because it had all these different fields in it, and you malloc size of struct node star, you're only allocating 8 bytes. And almost guaranteed when you start trying to use all the fields in that 1,000 byte node, you're going to seg fault. So making sure that you're doing that, and that's another thing malloc will complain about, is when you try to use that and you don't have enough space for it, it'll say allocated 8 bytes, but you need 12, basically. So those warnings from malloc can give you hints to things in your code that may blow up later on. But it doesn't always give you line numbers, right? So they're tricky to find sometimes. So I wanted to look at one example of some code. So this was a PA2. So I insert a 10, that looks fine. I print, that's a 10, that's fine. And then I try to, let's go ahead and insert a 20. So I've got a 10 and a 20, and then let's delete the first node. And valgrind is complaining. Okay, use of uninitialized value of size 8. And it's telling me it's in delete, but it's not giving me an actual line number. Okay, because this is running at runtime. And if I print my list, my 10 is still there, and I'm getting all kinds of backtalk from valgrind now, invalid read of size 4, and some other stuff. But also my 10 did not get deleted. So there's something going on here, right? But your first hint is really when I first tried to do this delete, it gave me some warning, use of uninitialized value of size 8, and it told me it was in delete. Okay, it told me the program counter, which doesn't really help me. But it tells me, okay, maybe I want to look at my delete function. So let's exit out of that. So let's go into GDB. So let's go into our Makefile. And this turned out to be one of those Makefiles where there were .c's in the dependency list. But regardless of that, what we want to do is add a -g switch to the compiler, right? So global substitution, just substitute GCC with GCC-G. And now we should be set to compile with debugging. So I'll remove PA2 and I'll say make, and it compiles it up with a -g. So let's GDB PA2. And there's something going on inside the delete function, right? So I want to stop when I get into delete. So I'll say break delete and then run. So I can insert a 10, I can insert a 20, I can print. Everything looks fine. So let's try to delete the 10. And it stops when I get in the beginning of my delete routine. All right, so I can list my code, and there's what delete looks like. And it's about to execute this temp equals list arrow next. So let's take a look at list. List is our sentinel node. So it contains a 2 and then a pointer to some other node. So I can print the thing pointed to by list arrow next. And that's a node containing 10 and a pointer to another node. And if I look at what that points to, that's a node containing 20 and a pointer of null. So our list looks great so far, right? We've got a sentinel with a 2 and a pointer to a node with a 10 and a pointer to a node with a 20 and a big null. It's a good list. So it's about to say temp equals list arrow next. So I can check temp before I do this. It's a 0. Let's go ahead and execute this instruction. And if I look at temp, it's the address of our first node. Right? It's the address of this node containing a 10. So we've got a while loop while temp is not null and temp arrow data is not equal to number. So let's print number. Well, that's a 10. Let's print temp arrow data. That's a 10. So this while loop is supposed to search for the number in the list, right? Because we put comments on it, so we know that. So while temp's not null, we're not at the end of the list, and we haven't found our number, we're going to go through this while loop. Well, we should kick out of this while loop immediately, which means we should come down to line 17. So let's go ahead and say next, and sure enough, that works fine. So it brings us down to where we're ready to delete the node. So if temp is equal to null, well, we check temp, it's not null. Okay, so that's fine, so we don't have to exit. So we say next, and now it says previous next equals temp next. That's where it's taking the previous node's pointer and having it point to the next node. So let's look at the value of previous, and it doesn't look like the other nodes, right? So let's see what's at previous. And it's got data of 41.97488 and next of some big long thing that it says is libc start main plus 240. And right there, something's not right. Okay. And this might seg fault when we try to execute it. It might work, but whatever happens, it's clearly not taking the sentinel and changing it to point to the 20. So we go ahead and we execute this instruction, and then we free temp, and then we're done. But list is still that, and it's still pointing to our next node, which has a 0 now. And that's pointing to our node with a 20. So what happened here? Well, when we were getting ready to say previous next equals temp next, previous didn't look like it had the right value, right? So let's look at our code. And previous is never initialized. It's given a value inside here, but in the one case where we don't actually go through our while loop at all, previous doesn't get a value. It's uninitialized, and when we do this to try to skip over our node, we're doing it to some other block of memory. So how could we modify this? In the one case where we're deleting the first element of the node, first node of the list, yeah, if we were to set previous to be where the sentinel is, man, you're bumming me out today. If we were to set previous to be the sentinel, then when we said previous next equals temp next, right, it would skip over that. So set previous equal to list. And there you go. So that's how you can use GDB, right? So valgrind or running your program tells you there's something going on. Valgrind can help pin it down a little bit, but then GDB can help you sort of figure out what exactly is going on. And it's really a matter of kind of stepping through the code, and you wrote the code, you know what it's supposed to be doing, right? So update your pictures as you go through the code, but at some point it's going to do something different. Right? And without having GDB in your arsenal, you're very unlikely to find that problem, right? That particular situation is so subtle, and in your mind, right, previous is always going to be the previous node. And most cases that you run through on paper, it's going to do the right thing, right? So you really need the computer to kind of like help keep you honest. Does that make sense? Does that help at all? So here's another version of a Makefile. And this is for that same project we just saw. But I'm defining a symbol here in the very beginning. My symbol is uppercase CC, and I'm setting it equal to little gcc. And anytime that I say $ parentheses CC, it substitutes the value of that variable in place. So down here where I say $ parentheses CC, that's going to get replaced with GCC. So this looks just like the previous Makefile, right? GCC-O, GCC-C, et cetera, et cetera. But now if I want to add debugging, all I got to do is this. Just change my symbol CC to be GCC-G. And now every time that I try to compile, it's going to say GCC-G. Or if I wanted to turn on or off some other option, right, I could do a similar substitution up there. Or you can globally substitute GCC with GCC-G like I did. But this makes it a little more nuanced. And this is set up so that the executable depends on the .os, and each of the .os depends on the .c and the include file, and has a command for compiling just as far as an object. And this also has a clean option, so if you say make clean, it'll get rid of everything that was compiled and linked and give you a clean slate. All right, good. So your midterm is in 1 week, and it's going to be mostly programming. Okay, I'll probably throw some concept type questions on there, but it's going to be mostly writing pieces of code. And it'll definitely involve linked lists, and it'll probably involve stacks and queues. It will not involve trees, which is what we're going to start talking about today. So I want to have trees on there, but it'll have lists, and it will have structure statements, and it will have pointer dereferencing and all the stuff that we've been doing this quarter. So Wednesday, I'll do a bit of I'll post something up on Canvas, which is kind of a review of topics, but you've been doing this stuff intensively for 5 weeks, so you probably have a pretty good idea what we've been doing. But I'll put up a study guide see if there's any questions. All right, so ready to switch gears? So we've been doing linked lists, and we were using linked lists as a way to store information. And we got to linked lists by looking at arrays and noting that arrays were inefficient in some cases. If you have an array of numbers and you want to add a new number to your array, if you stick it in the end, it's very quick. You just copy it into the next location that you're not using in the array, and you're done. If you want to delete something from your array, you could either choose to ignore it, somehow remember I'm never going to use this element, or you could take everything that comes after that and shift it up one spot, right? And then say I've got one fewer things in my entire array. But if you're trying to keep your data in some sort of sorted order, insert becomes painful also, because if you want to insert something close to the beginning of the array, you've got no choice but to move everything below that down to make space for the new entry. And that's expensive. For a list, an array of n items, it takes you roughly n operations. So it's an order n. So a sorted array so insert is order n, and delete is also order n. But how long does it take to search for something in a sorted array? Does it take n operations? It's better than n, right? So we could play high-low. If our data was sorted, we could start in the middle, and we could restrict our search to either the first half or the second half. And based on that, we could look at the point in the middle and restrict it to either the first quarter or the second quarter of the list, or the third or the fourth. So search was order log n. And that's nice. Say again? Yeah. Best case would be 1, right? Your number's right in the middle and you guess it first try. All right, so we switched to linked lists. And if we know where to insert, right, if we're sitting somewhere in the middle of the array and we want to insert, it's an order 1 operation, but order n to find the insert point. And delete is exactly the same thing. The actual deleting of a node only takes three steps, right? Take the previous node, point to the next node, and free this node from memory. But to get to the point where we want to delete the number, that can take n steps because we start at the beginning and we move forward. And more generally, search is clearly order n because we have to start at the beginning and move until we find the number or we get to the end of the list. So, and the inefficiency of insert and delete is basically searching for the place where we want to insert or delete. So search is really the key. This has like bottlenecked our performance. And the problem is we can't play high-low on a list. Now, why can we play high-low on an array? Because if we know that our array contains 100 things, we can say, show me element 50. And we know that's the middle number. And if that's too big, we can say, show me element 25, because that's the middle number of that upper half. So those indices make our life nice, but they hurt us when we try to insert. So the idea is, can we somehow combine these and get the best of both? Nope, we can't. We're done. See you tomorrow. So yeah, there is a solution, and this is what a tree will do for us. So here's how this works. Suppose we have a set of numbers. I don't know why they're all multiples of 5. We have a set of numbers, and they're stored in a linked list. Okay, and we want to search for something efficiently. Well, we have to be able to find the number that's in the middle of this list, right? So what we're going to do is we're going to save a pointer to that middle node. That's actually going to be where we start our access to this list, is with the middle node. Now, say we're searching for a number that's bigger than 40. Then we know it can't be any of these nodes over here to the left of this middle point. It's got to be somewhere here in the right. And we'd like to search this efficiently, so we'd like to know where the middle of this smaller list is. So we're going to want a pointer to the middle of this list. And similarly, if our number was smaller than 40, we'd want a way to get to the middle of this sublist. So we want a pointer to this node. But where should we put those pointers? Because we don't want to just have a big array of 1,000,000 pointers, right? So we're going to put those pointers right next to this middle node. So we're going to start our list access at this node that's in the middle, and it's going to have a pair of pointers. One that points to the middle of the list on the left, one that points to the middle of the list on the right. And each of those nodes is going to have a pair of pointers, one that points to the middle of the list on the left, and one that points to the middle of the list on the right. And those lists on the left and right are just single things now. But same thing with the 60, it'll have a pointer to the 45 and a pointer to the 75. But if these were much bigger lists, right, they would have gone into the middle, and those middle elements would have pointers to the middle of the two sublists on either side, and so on. Okay, so we're going to use 2 pointers per node, and instead of pointing to the next node in the list, it's going to point to the middle of the sublists on the left and the right. It could be a housekeeping nightmare, but it's going to be really nice to use because it's going to let us do this high-low when we're searching for things. Okay, so let me draw this in a different form. So this looks a little more believable now. But it's the exact same collection of pointers as in that linked list. But this is typically what you'll see when you're looking at a binary tree. Okay, so that's our setup. We're after a way to build something like a linked list, but where each node has a pair of pointers pointing to the midpoint of the sublists on either side. And this is going to be the case for every node, except for these ones down here, which have no sublists on the left or the right. All right, so that's going to be a binary tree. Yeah, I was careful to do 2 to the n minus 1 here. But the only thing that happens if you have something other than this number of elements is, for example, if we had an 80 over here along with a 75, what's the midpoint of that? Well, it's kind of in between, but not really. So we could go to either the 70 or the 85, and we get a slightly different looking tree. So we'll see details of that in a bit. All right, so this is a binary tree. Binary because each node has no more than 2 arrows coming off of it. Okay, a ternary tree would have 3 pointers coming off of each node. So we're going to mostly talk about binary trees for now. So each node has a pair of arrows. And technically, since every node has arrows, all right, this is what our tree looks like, but these are all null. And pointers to null we usually don't draw. All right, so let's do some terminology. So this node where we begin our access to the tree, this is called the root. When you have a relationship like this, we say 60 is the parent of 70. Bless you. And we can also say 70 is a child of 60. So we think of like an ancestry tree. So 60 is a parent of 70, 70 is a child of 60. In another few weeks, we'll also talk about siblings and grandparents, because we'll actually need those for doing some operations. But for now, it's just parent and child. All right. A node with no children is called a leaf. So a node with no children. These are called nodes, by the way. Right, so nodes are just the things that make up our tree. And so a root is the one and only node with no parent. So this is the node with no parent. Every other node has a parent, right? It's further down in the tree. And every node has children except for the leaf nodes. All right, so the depth of a node is the number of edges from the root to that node. So this 20 has a depth of 1. Because from the root, we have to follow one edge to get to it. This 10 has a depth of 2. And the root has a depth of 0. because we don't have to travel any edges to get from the root to the root. It's going to turn out an empty tree that does not even have a root. We're going to define its depth to be -1. And that's just going to make life really good. But it won't make sense in terms of this definition. But for now, depth is just the number of edges from the root to that node. And then the height of a tree equals the depth of the deepest nodes. So you find the height of find the depth of every single node in the tree. Whichever depth is the greatest, that's the height of the tree. So for example, this tree has height 2. Because the deepest nodes have a depth of 2. Still with me? All right, just definitions and terminology. All right, we can also talk about subtrees, because a tree actually contains other trees inside it. My laptop actually contains a laptop inside it somewhere. Close enough. So this whole thing is a tree, but this thing is also a tree. Right? It's binary. Each node has no more than 2 children. It has a root, which is one node with no parents. It has some leaf nodes down here. This is a tree whose height happens to equal 1. Right? But it's a tree contained inside this bigger tree. So this is a subtree, kind of like a subset. All right, parent has children, so we talk about the left child and the right child. So 50 would be the left child of 60, and 70 would be the right child of 60. We don't have a left and right parent because we only have one parent. But parents can have multiple children, so the one on the left and the right, we call them accordingly. And this subtree would be the left subtree of the node 40. There's also a right subtree. And each subtree also contains further subtrees in general. Right? And this is going to work really well when we start talking about recursion and using recursion to do things to trees. Because the pieces of a tree will also be trees, right? A subtree is a tree. And if we know how to do something on a subtree, a lot of times we'll know how to do something on the larger tree. And this is going to fall right out of inducting on the height of the tree. All right, so we've got subtrees. And all the trees I've drawn so far have had a particular characteristic, which not all trees will have, right? We haven't put any requirements on the nature of these numbers in the tree. They could be any random numbers. But in fact, I've been drawing a particular type of tree, which is called a binary search tree. And a binary search tree is a tree that you would get by starting with an ordered linked list and then making those pointers point to the middle of the subtrees on the left and the right. So if we have a BST, we have some nice properties. For example, at the root, every node in the left subtree is smaller than the value of the root. And every node in the right subtree is bigger than the value in the root. And I'm assuming there's no duplicates here, just to make things easier. So every node in root's left subtree is less than the root, and every node in the right subtree is bigger than the root. And that's only true with binary search trees, right? In an arbitrary tree, there's no reason that has to be the case. But the trees we're talking about for the next few days, this will always be true. And since a subtree is itself a tree, we're going to have that same property. For example, if we look at this 20, everything to the left of that's going to be smaller than 20. Well, there's just a 10, so that's certainly true. And everything to the right is going to be bigger than 20, 25 in this case. But we could hang more things off of this, right? And guaranteed everything over here is going to be bigger than 20. And if I look at this subtree, here's a root, everything to the left has got to be less than 25. And this is the property of binary search trees that's going to make everything else we're about to do tomorrow possible. Okay, primarily searching efficiently. But that also makes it possible to insert and delete efficiently. All right, that's our setup. So we'll start looking at some algorithms for working with trees tomorrow, and then we'll look at some data structure aspects of this. We'll see what a node would look like in a structure statement, and then we'll start talking about recursion and how to process these things without having to write more than like 2 lines of code. So that's where we're heading. All right, I'll see you tomorrow.